Last time we talked about binomial coefficients and numbers of subsets of sets, and today I want to look at generating functions for subsets and the related elementary symmetric functions. So let's look at the polynomial which is a product of factors of the form 1 plus xi z. So this is a polynomial in z of degree n. The constant term is 1. Coefficient of z, well, maybe it would help if we write this out. So 1 plus x1z, 1 plus x2z, 1 plus x3z, etc. So if we want to pick 1z, I guess we're going to pick 1's from every other factor. That'll give us a coefficient of x1 if we pick this z, or x2 if we pick that z, or x3 if we pick that z. So in other words, we'll get the sum of all the x variables. And if we look at the coefficient of z squared, we'll get a z squared if we pick two z's and all 1's from the other factors. So that'll give us x something and x something else. So x1, x2 plus x1, x3 plus x2, x3, etc. depending on which two z's we pick, and of course we pick all possible pairs. And similarly, the coefficient of z cubed is the sum of all possible x values, x variables 3 at a time. And in general, the coefficient of z to the k is the sum of products of k different variables at a time, where these indices I1 through Ik are at least 1, and all different because we're never going to pick any x variable twice. And they're at most n. This coefficient is called the kth elementary symmetric function in x1 through xn. Now, what is the elementary symmetric function? Well, it's basically a list of subsets. Here we've got a list of all the one-element subsets. Here we've got a list of all the two-element subsets. Here we've got a list of all the three-element subsets, and in general the k-element subsets. So it makes sense that if we set xi equal to 1, then we're going to count the one-element subsets, 1 plus 1 plus 1 plus 1, 1 for each subset, and count the two-element subsets, 1 squared plus 1 squared plus 1 squared. 1 squared is 1, of course, so we get 1 for each two-element subset. If we plug in xi equals 1, then here we get 1 for each three-element subset. So that means that 1 plus z to the n is the sum of and choose k z to the k. K equals 0, corresponding to the constant term, which I guess I erased or didn't write down. And of course z to the n is the greatest coefficient we see. That means if we ever see a polynomial of the form 1 plus something z squared, then the coefficients are elementary symmetric functions in something. Almost the zeros of the polynomial, but not quite. Let's look at that closely. Let's factor p of z equals 1 plus a1z plus a2z squared, etc. Let's say it's degree n. Now if we factor over the complex numbers, we know that every polynomial factors completely. So we're going to get factors like this. So that means that the kth coefficient is the kth elementary symmetric function in these numbers b1 through bn. Now these are not zeros of p, because 1 plus beta I is not necessarily equal to 0. But the zeros of the polynomial are the numbers z that make these factors equal to 0. So if we set z equal to -1 over beta I, then we have 1 plus beta I -1 over beta I. Beta i's cancel, 1 plus -1 equals 0. So these numbers beta are opposites of the reciprocals of the 0 of the polynomial. And I guess you might say, well, how do we know beta I is not 0? Because I'm dividing by it here. Well, if beta I were 0, then 1 plus beta iz would be 1 plus 0z, which would be 1. And if we have n factors of that form, and they're not all different from 1, then we wouldn't be getting a polynomial of degree n. If one of these were just 1, then we'd have n minus 1 other factors that were not 1, and we'd have a degree n minus 1 polynomial. Now let's consider the infinite product of 1 plus xiz. So the same as before, except we're not letting I go from 1 to n, but 1 to infinity. So consideration of the coefficients is pretty much the same as before. Now the coefficient of z to the k is the sum of all possible sequences of k indices of products of x with subscripts equal to those indices. So this is the sum of all possible monomials of degree k with different variables. So a sum of all possible products of different variables k at a time. This is the kth elementary symmetric function in infinitely many variables. The end.